Welcome to the online lecture series of heat and mass transfer. Here is Professor Lakshman Mani. This is a video session on heat transfer analysis of long fin with insulated end tip. So here, this is a case 2 of the differential equation for rectangular fin. In that, we have to find equation for heat transfer flow rate from long fin. Now, in case of long fin, practically heat loss from long fin at end of tip is negligible. Hence, it is considered as insulated. So here in this diagram, you can see here this is a fin of length L. Here this is the base of fin. This is end of fin. So Q is a heat flow from the base and QC is a heat transfer from the fin to the surrounding by convection. So here now we can see this is the base of fin. So distance from the base of fin toward the end of the fin is shown. So at the base x is equal to 0 and at the end x is equal to L. Now in this case we will have temperature distribution. So here this is a vertical axis which is used to show the temperature. Horizontal axis is used to show the distance along the fin. Now at the base temperature is higher because of heat source. So at x is equal to 0, temperature is T0. Now as the distance from the base increases towards the end of fin, here temperature will be reduced. That's why here temperature profile is in this way. So at the end means at x is equal to L, temperature is TL. Now here at x is equal to 0 means at base we say temperature of fin surface is a T0. Now in this case theta is temperature gradient, means temperature difference between fin surface temperature and surrounding temperature. So at the base this theta we will show by theta 0. So what it will be? At the base temperature is T0, surface fin temperature, and ambient temperature is T infinity. Here we will write, this will be ambient temperature. So temperature between TO and T infinity, that is theta 0 at the base. Now at the end, here the temperature is reducing in such a way that from T0 to TL, at the end of fin, this TL is going near to T infinity. It tends to T infinity, means temperature of surrounding. So that's why here theta is equal to TL, means fin surface temperature, minus T infinity means ambient temperature, that becomes 0. Means here theta temperature gradient we get at the end of fin as a 0, and that's why end of tip of fin is considered as insulated. Now we will see the further part of the equation. So this derivation will have two parts. Part A will be temperature distribution. That will be obtained by using boundary conditions. So here for temperature distribution, for temperature distribution. Now let us, here will be two boundary conditions as we already have discussed, at the base and at the tip. So at base, x will be equal to 0 and temperature of fin surface will be considered as a T0. Then theta 0 means temperature gradient at the base will be what? T0 minus T infinity. Then second will be boundary condition at end of fin or at tip. So there x will be what? L, that is length of fin. T, temperature of fin surface at the end will be TL, and that tends to T infinity. So that's why here in this case theta means TL minus T infinity will be equal to 0. Now as theta is 0, so here d theta by dx means temperature gradient, that will be 0. So as temperature gradient 0, that's why in this case here heat flow rate at the end of tip will be 0. Now we can have here equation, that is general solution, that already we have studied in the video of differential equation of rectangular fin. So the general solution is theta is equal to C1 into e raised to mx plus C2 into e raised to minus mx. Say this will be equation number 1. Now we have to find value or expression for C1 and C2. So for that apply boundary condition. So here now applying boundary condition, one means at x is equal to 0, t is equal to t0, that we have to apply. So in this case theta will be what? 0. Theta 0 is equal to C1 into e raised to m into x value at first boundary condition is 0 plus C2 into e raised to minus m into 0. So in this case here what will happen? C1 into e raised to m into 0 means 0, e raised to 0 means 1 plus C2 into, again here this product will be 0, e raised to 0 means 1. So here we will have theta 0 is equal to C1 plus C2. We will get this equation that we say as a equation number 2. Now differentiate the above equation, equation 1. So here differentiate equation 1 with respect to x. So with respect to x, if we differentiate, then we will have the equation that will be d theta by dx is equal to, now differentiation of the equation d theta by dx is equal to C1 into differentiation of e raised to mx. So C1 into e raised to mx, this will be differentiation, into differentiation of mx. So x derivative will be 1 into m. So here m will come, plus C2 into e raised to minus mx. C2 into differentiation of e raised to minus mx, that is e raised to minus mx. Derivative of minus mx will be what? Minus m. So here we will have this m into C1 into e raised to mx. This minus sign will come here. This will be what? Equation, say equation 3. Now applying boundary condition 2, this equation, that is equation 3. So boundary condition 2 is what? You can see here. This is second boundary condition. At the end x is equal to L. Here d theta by dx is a 0. X is equal to L and d theta by dx is equal to 0. So here d theta by dx is equal to 0 is equal to m1 c1 e raised to m into x is L minus m c2 e raised to minus m into x is L. So here we will have 0 is equal to m1 c1 e raised to ml minus m c2 e raised to minus ml. So this term we can bring on the left side of the equal sign. So here c1 e ml e raised to ml, this m1, that is equal to, this is not m1 actually, this is only m, is equal to mc2 e raised to minus ml. So in this case here m on the both side will get cancel. So we will have the equation c1 e raised to ml is equal to c2 e raised to minus ml. So we can write this equation in the form of c2. So c2 will be equal to c1 into e raised to ml divided by e raised to minus ml. Say this equation number 4. Now this value, C2 value, we can put in equation 2. So equation 2 is theta 0 is equal to C1 plus C2. So we can put now the value of C2 in the above equation, that is this equation, equation 2. So here putting C2 value in equation 2. So what we find? Theta 0 is equal to C1 plus C2, and value of C2, that is C1 into e raised to ml by e raised to minus ml. Simplifying this equation means here we can take LCM. Here is divided by 1. So LCM will be at the denominator e raised to minus ml. Now here product of C1 and this term, C1 into e raised to minus ml plus this term C1 into e raised to ml. Now in this case C1 is here same, so we can take common C1. So next step will be theta is equal to C1, we can take common in the bracket e raised to minus ml plus e raised to ml divided by e raised to minus ml. Now this equation we can write in the form of C1. So C1 will be equal to what? This right side term, if we bring on the left side of this theta 0, so it will become theta 0 into bracket e raised to minus ml divided by e raised to minus ml plus e raised to ml. This say as a equation number 5. Now here we can put this value C1 from this equation 5 in equation 4. Means here this is equation 4, C2 is equal to C1 into this. So here this C1 value we can write, or we can put this expression. So putting C1 in equation 4, we get C2 is equal to theta 0. So value of C1, here what we have to write? C2 is equal to C1. So C1 expression first we will write, that is theta 0 e raised to minus ml divided by e raised to minus ml plus e raised to ml. This is a expression for C1. Okay, into next part, this as it is, so that is e raised to ml divided by e raised to minus ml. So here now in this case, this e raised to ml term and this e raised to minus ml and this e raised to minus ml, these terms will get cancelled. So what remains, that is C2 is equal to theta 0 bracket e raised to ml divided by e raised to minus ml plus e raised to ml. So we here obtain expression for C2. This is what equation number 6. Now we have expression for C1 from equation number 5 and expression for C2 from equation 6. Now we can put these equations or expressions C1 and C2 in main equation, that is general solution, that is this theta is equal to, this is general solution. So here is a C1 and here is a C2. So we can substitute C1 and C2 in the equation number 1. So putting expression of C1 and C2 in equation 1, we have theta is equal to, this is a C1 into mx and this is a C2 into e raised to minus mx. Next, this theta 0 is a common we have taken. So inside the bracket, product of this e raised to minus ml and e raised to mx is here, and product of e raised to ml into e raised to minus mx here. At the base, this denominator here and this denominator here. If you observe, this denominator is same, both expressions. So we can take summation of these upper terms. So then we can take this theta 0 on the left side. So theta upon theta 0 is equal to sum of these upper terms divided by this denominator common, e raised to minus ml plus e raised to ml. Then we can observe here this m is a same, so we can take common. So at the numerator, e raised to minus m bracket L minus x. Similarly here m is same, we can take common, bracket L minus x. At the denominator, e raised to minus ml plus e raised to ml. Now what we do, we divide numerator and denominator by 2 so that we can reduce this equation. So for that purpose, then we take this equation. So here we find theta upon theta 0. We divided this numerator by 2 and denominator by 2. Then in the mathematics, we have the mathematical equation e raised to minus a plus e raised to a divided by 2. For this we can write cos h of e. So whenever there is a e raised to some term as a, so here we will have here this a term, this is a term at the numerator. Similarly here at the denominator, means we can write for this cos h of e. So from that point of view, here theta by theta 0 left side is equal to cos h, means this cos h And for A, for the numerator we can write m into L minus x. So m into L minus x divided by cos h bracket for the A at the denominator, this is ml. So we can write this ml. So we find this formula, say this equation number 7. This is the equation for temperature distribution. This is the equation for temperature distribution. Now this is part A, boundary condition for temperature distribution. Now part B is heat flow rate from fin. So for that now we will proceed for the further equation, heat flow rate from fin. So for that we will have here theta is equal to T minus T infinity and theta 0 is equal to T0 minus T infinity. This is temperature gradient, already we have discussed at the start of derivation. Temperature gradient at the end of fin, T minus T infinity, and at the base, T0 minus T infinity. Now, as per this, equation number 7, we can once again write. So, theta upon theta 0 is equal to this. For theta we can write here, and for theta 0 we can write this is equal to earlier equation number 7. This equation is also equation of temperature distribution. Now at tip of fin we have x is equal to L and t is equal to TL. That already we have seen in the start of the derivation. At this, at the tip here, x is equal to L and temperature is TL. So we can now put x is equal to L and t is equal to TL in the above equation. So now we will have the equation T is equal to TL minus T infinity divided by T0 minus T infinity is equal to cos HM inside the bracket L minus x value is L divided by cos H ml. Now here L minus L will be what? 0. So here cos HM of 0 divided by cos H ml. So here cos HM of 0 will be what? 1. So TL minus T infinity divided by T0 minus T infinity will be equal to 1 upon cos H ml. This, say, equation 8. Now heat flow from the fin can be given by the formula, that is Fourier's formula. heat flow from fin. It can be given by the formula Fourier, that is Q is equal to minus K thermal conductivity into area into temperature gradient d theta by dx at x is equal to 0. So this we say as equation 9. Now equation 7, in that once again we will write equation 7 here. Theta upon theta 0 is equal to cos h. This is equation 7. This equation once again we will write and this equation we will arrange in this way. Theta is equal to theta 0. This right side we will take inside the bracket. In this way. Now differentiate this equation. With respect to x. Why? Because we have to obtain d theta by dx. For this we can differentiate this equation with respect to x. So we find here on differentiation d theta by dx is equal to theta 0 here as it is. Now in this case cos differentiation will be what? Minus sign, and this m will be here, so minus m into sin h m l minus x. In this way differentiation will come, and now this d theta by dx we got. This we will say as a equation 10. Now putting this d theta by dx expression in 9. At the place of d theta by dx we can write this right hand side. So we can have further part. Q is equal to minus k to a theta 0 bracket minus m sin h m l minus x divided by cos h m l at x is equal to 0. Okay, now we have to put x is equal to 0 here. So minus k into a into theta 0 bracket minus m sin h m l minus x value is 0 divided by cos h m l. So here we have next step minus m sin h ml divided by cos h ml. Now sin HML divided by cos HML means tan HML. Sin upon cos ratio is a tan. So we can have here Q is equal to, now this minus K and this minus M. So here minus minus will plus. So K into theta 0 M tan H ml. This will be the equation. Now next to this, as in last video we have considered M is equal to HP by KA. So the above equation here we can write HP by KA at the place of M. So here KA theta 0 into the square root of HP divided by square root of KA, we will write in this way, tan HML. In this case, the square root of K will get cancelled with this term. So remaining term, that will be Q is equal to square root of K will come here. So this square root of K and this square root of HP we can write together, HP K square root into theta 0 as it is into tan H ml. So this will be the equation for heat flow rate from the long fin. So this is what heat transfer or heat flow long fin with insulated tip. Now here we will have one graph that will be the third part graph, which will give variation, means change in heat flow with changing value of ml. So that graph we will show here. So here we will take 0.5, 1, 1.5, 2, here 2.5 and here 30. On the upper side here will be 0.2, 0.4, 0.6, 0.8 and 1. This will be the scale. Now this horizontal scale we will use to show value of ml, and this vertical scale we will use to show the heat flow. So in this case we find the curve in this way, that is a curve for tan ml, curve for tan ml. So from this what we see here as first observation, as value of ml increases, Q increases. So as ml increases, heat flow increases. Second observation, at ml nearly equal to or equal to 3, this curve becomes asymptotic. Means at ml is equal to 3, here fin is called as fin with insulated tip, fin with insulated tip or adequately long fin. Adequately long fin. So these are the three observations we have from this graph for the insulated long fin. So this is a C part. So in this way we have seen today part A for temperature distribution, part B for heat flow rate, and part C for variation in heat flow rate with value of ml. In this way we can see the other derivations of heat and mass transfer. So for that, subscribe the channel Thermal Engineering and enjoy the video sessions of the different subjects. Currently we have video sessions on heat and mass transfer. Thank you.